What is the qth Fibonacci number where q is rational? This is a joint work with Buket Eren Gökmen from Graz University of Technology. So the answer to the question is the codenominator function. If x is a positive rational, then the Fibonacci number of index x is going to be defined to be a positive integer. And this function f is going to be called the codenominator function in the SQL. Let's start with the numerator function. We all know what it is. If x is written in a reduced form p over q, then the numerator of p over q, numerator of x, is just p. This numerator function satisfies the functional equations. Numerator 1 plus x equals numerator of x plus numerator of 1 over x. And numerator of x over 1 plus x equals numerator of x. Notice that this is just, in fact, the denominator of x. In fact, these equations determine the function numerator completely on the set of positive rationals. The numerator satisfies the additional functional equation, numerator of x equals x times numerator 1 over x. Indeed, this is equivalent to saying, this equation says that x equals numerator of x divided by the denominator of x. Let's check these equations for the numerator function. If we set x equals p over q again in a reduced form, then the numerator of x plus 1 equals numerator of p over q plus 1, which equals numerator of p plus q over q, which equals q plus p, what we have here. And what is p? P was the numerator of x, and q here was the denominator of x, which is just the numerator of 1 over x. So we get the first functional equation, numerator of x plus 1 equals numerator of x plus numerator of 1 over x. What about the second equation? Numerator of x over x plus 1 equals numerator of p over q plus 1. If you multiply both sides by q, then we get p over p plus q. And the numerator of this is just p, because these two numbers are coprime if p and q are so. So here we have our functional equations for the numerator function again. And I want to modify this system just a little. So the first equation is going to be the same. But in the second equation, I'm going to replace this x by 1. And we impose the initial condition f1 equals 1. One can show that this system is coherent, first of all. So it admits a solution. And once we define f1, then we can define compute f in terms of f1. So the solution is unique if we fix f1 equals 1. And we call its solution the conumerator function and denote as con from the set of positive rationals to the set of positive integers. The codenominator function is defined to be the conumerator of 1 over x. So f of x equals conumerator of 1 over x. We can rewrite the defining system of functional equations for the conumerator, which gives this system of functional equations for the codenominator function. So the first equation becomes the second equation becomes f1 plus 1 over x equals f of x. And if we substitute 1 over x instead of x here, this equation is equivalent to f1 plus x equals f1 over x. And the second equation is f1 over 1 plus x equals fx plus f of 1 over x. And we have our initial condition, f1 equals 1. Now, let us look at the functional equations. So from this equation, if I write x plus 1 in place of x, we get f 2 plus x equals f 1 over 1 plus x, which is precisely what I have here. And so this equals f of x plus f of x plus 1. Why? Because f of 1 over x equals f of 1 plus x. So this gives the equation f of 2 plus x equals f of x plus f of x plus 1 with the Fibonacci recursion with the initial condition f1 equals 1. This is precisely the Fibonacci recursion, and we see that f of n equals the nth Fibonacci number fn. So we see that the codenominator function extends the Fibonacci sequence to q. So fn equals fn. And what about the connumerator function? Connumerator of x equals f of 1 over x by definition, which equals f of 1 plus x. So the connumerator is just the Fibonacci sequence shifted by 1. It is f n plus 1. Now we can iterate these functional equations to get the following result. First of all, f of n plus x equals the nth Fibonacci number times f of 1 plus x plus the n minus 1th Fibonacci numbers times the codenominator of x. And similarly, if we iterate the second functional equation, we get that the codenominator of fn plus 1x over fn minus 1 plus fn x equals f of x. Again, if we take a look at the functional equations, we can observe this. So if I iterate this functional equations, this functional equation, if I iterate this functional equation, so this gives f1 plus 1 over 1 plus 1 over x equals f of 1 plus 1 over x, which equals f of x, etc. And if we iterate this again and write this in a compact form, we obtain the second functional equation here. And from this, it turns out that the codenominator of fn over fn plus 1 is just n. And the codenominator of fn plus 1 over fn is 1. The codenominator of 1 over n is just fn plus 1. Let us denote this continued fraction by this form. Then we can use the lemma to compute the codenominator of this rational number recursively. It's a simple application of the lemma. So the f of n0, etc., nk equals the n0th Fibonacci number times this continued fraction plus n minus 1th Fibonacci number times this continued fraction. In particular, the codenominator of half positive integers equals fn minus 1 plus fn plus 1, which is the Lucas number. So we can define the Lucas function on the set of positive rationals as Lucas of x equals 2 times codenominator of 1 over x minus the codenominator of x. So we are also able to extend the Lucas function to the set of positive rationals. Let us give some examples. For example, if 23 over 31 is 107, which is a prime number. 31 over 23 is 47, which is also a prime. 19 over 41 is far from prime, even though these are all primes. And 41 over 19 gives 3 to the power 4. It is also far from being prime. I can provide you also a list of the codenominator values of some numbers, some rationals of the form 41 over n, where 41 is just an arbitrary number. You can observe several facts. In fact, we see that there are many numbers, and these are not all Fibonacci numbers. And it turns out that any number, fn, in fact, the function f of x can attain any value, any positive integral value. So any number, any positive integer is the Fibonacci number of some positive rational. Well, what is nice about the codenominator function is that we can express the numerator function in terms of it. The numerator of x equals the codenominator of f of x over f of 1 over x. And this fact has a rather straightforward proof. You just show that this function here satisfies the functional equations for the numerator function. And from this, we get that the codenominator function satisfies an additional functional equation. Because if I put 1 over x here, then this is going to be 1 over x, and here we are going to have x. And so x equals this expression divided by this expression, but with x replaced by 1 over x. We also introduce another function, which is quite useful when dealing with the codenominator function. It is called the codiscriminant function. It is f1 over x squared minus f of x times f of 1 over x minus f of x squared. We can easily show that, first of all, this function is two-periodic. So codiscriminant of 1 plus x equals minus codiscriminant of x. And the codiscriminant of 1 minus x equals codiscriminant of x. So this is also a nice function with integral values on positive rationals. And this periodicity here is equivalent to the Cassini identity, in fact. When n is integral, positive integral, then the codiscriminant of n from this definition equals f of 1 over x squared. But recall that f of 1 over x is just f1 plus x, which is just the n plus 1 Fibonacci number. So here we have this expression. And by doing the same thing here, we get that the codiscriminant of n is fn plus 1 squared minus fn plus 1 fn minus fn squared, which is minus 1 to the power n. We can use the codiscriminant function to generalize many Fibonacci identities found in the literature. One idea for generalization is to replace, whenever we have a formula involving the Fibonacci numbers, we replace fn by f of x, and often we have minus 1 to the power n somewhere in the formula, and we replace this by the codiscriminant of x. Here is an example. Suppose that at least at least two of x, y, and z are integral. Then we have f of x plus y times f of x plus z minus f of x times f of x plus y plus z equals the codiscriminant of x times fy times fz. When x, y, and z are both integral, then this is the usual Taguris identity. And moreover, by further specializing this formula, we obtain Dokkain's identity and the Catalan identity. So this is a generalization of the Taguri identity to the codenominator function. And you can pick any formula found in the literature and ask yourself if it admits an analog for the codenominator function. Now we are going to introduce a function by using the codenominator function. It is also initially defined on the set of positive rationals, but we are going to extend it to the set of real numbers. It sends x to f of 1 over x divided by f of x, which is in place of f of 1 plus x equals f of x plus 1, so we can write this in this form as well. And its plot looks like this. It is initially, as I said, this is defined on the set of positive integers for the moment. So it has many jumps. It appears to be discontinuous. We can prove the following assertions about this function Jimm. First of all, this function is involutive. Secondly, f of 1 over x equals Jimm of 1 over x equals 1 over Jimm x. This is quite evident from the definition. It follows easily from the definition, because what is Jimm of 1 over x? It equals f of x divided by f of 1 over x, which is nothing but 1 over Jimm of x. So, moreover, again, by using the functional equations for the codenominator function, we can show that Jimm of 1 plus x equals 1 plus 1 over Jimm x. And furthermore, Jimm of 1 minus x equals 1 minus Jimm of x. So this equation says that, in fact, these two equations, the involutivity says that this graph is symmetric with respect to this axis. And the equation Jimm 1 minus x equals 1 minus Jimm x says that the graph is symmetric with respect to this axis. So this plot is symmetric to both these axes. Now, once we prove the following, once we prove these functional equations for the Jimm function, we can compute the value at any rational given in the continuous fraction form as follows. Here I have my continuous fraction. To find Jimm x, what do? Instead of n naught, I write n01 minus 1 once. So I write 1, 1, and 0 minus 1 times here. And then I put 2. And again, I replace n1 by a string of 1s, but this times of length n1 minus 2. And I do this again, the same thing, and 2 minus 2, etc. up until the last index. I mean, right before the right index. And for the last index, I do the same that I did at the start. So I replace nk by a string of ones of length nk minus 1. So when we apply this formula, if n1 is 1, for example, then I'm going to get 1 minus 1 here. So a string of ones of length minus 1. What does this mean? And sometimes I'm going to have 0. If n1 is 2, for example, then I'm going to have 1, 0 here, 1, 0 here. In order to deal with cases, we have the following rules. First of all, if I have 1 sub-0, then we just ignore it. And we have 1 minus 1. We just replace this part of the sequence with n plus m minus 1. So this is how the value of Jimm is defined on a given positive rational. And it's a simple consequence of the functional equations. Now we can extend this function Jimm to the set of non-zero real numbers. First of all, we extend Jimm to the set of negative integers, negative rationals, by setting Jimm of x equals minus 1 over Jimm of minus x, whenever x is negative. And then we extend it to the reals by continuity. So Jimm of y is defined to be the limit. We can show that this limit always exists, and in fact it is easy to observe this from this formula, that this limit exists. And the extension satisfies the following functional equations on all non-zero real numbers. First of all, Jimm of 1 over x equals 1 over Jimm x. So this says that Jimm commutes with the operator or the function 1 over x. Similarly, the second equation says that Jimm commutes with the involution 1 minus x. And finally, this equation says that Jimm does not commute with the involution minus x. So we don't have Jimm of minus x equals minus of Jimm x, but something a little different. In fact, these equations says that Jimm acts as the auto-automorphism group of PGL2Z because the operators 1 over x, 1 minus x, and minus x generates the group PGL2Z. And you can show that these equations define the auto-automorphism of this group. So this function Jimm is a kind of modular function because of the functional equations it satisfies. It's a kind of covariant function, not invariant, but a covariant function. And it is rather easy to prove that this function is continuous on the set of non-rational numbers. So whenever we have an irrational point, this function is continuous. And as you see, it has jumps, and these jumps appear at rational points. At every rational point, we have a jump. And by concentrating on these places, it is easy to guess that this function must be differentiable almost everywhere, and this derivative must vanish almost everywhere. I don't claim that the derivative vanishes whenever it is defined. It may have points where the derivative is defined, but it is non-zero. But almost everywhere, except on a set of measure 0, the derivative vanishes. And this function also, it is again straightforward to prove from the expression for Jimm x, where x is given in the continued fraction form. It is easy to show that this involution sends quadratic irrationals to quadratic irrationals. And Jimm also commutes with the Galois conjugation on quadratic irrationals. This says that suppose that x equals alpha plus beta square root of gamma, where alpha, beta, gamma are some rationals, where gamma is a positive rational. Positive rational, gamma is not a square. Then Jimm sends this quadratic irrational to another quadratic irrational, theta plus eta square root of kappa. And the claim of conjugation with the Galois action says that Jimm sends the Galois conjugate of this to the Galois conjugate of this. And finally, what happens if x is not a rational, not a quadratic irrational? If it is an algebraic number of degree higher than 2, then the value of Jimm at this point is a transcendental number, conjecturally. So let me give some examples on square search, quadratic search. As you see, this is nothing simple or evident, the images. It needs some work to compute these values. For example, the value of Jimm at square root of 7. It is 1 over 6 times square root of 37 plus 1, etc. So Jimm is not at all a trivial function on the set of quadratic irrationals. Now, as I said, the Jimm has jump discontinuities at rational points, and we can compute this in terms of the function codiscriminant that we had defined earlier. If x is greater than 1, and we can compute this for other values of x well, but in the specific case, the jump of Jimm at this continued fraction is minus 1 to the power n0 plus nk times square root of 5 divided by the codiscriminant of the reverse of this number. So we reverse this number and we take the codiscriminant and we get the jump of the function Jimm at that point. Let me give you a few more examples to conclude. Jimm of the third root of 2 is some weird number like this. And as I said, this is conjectured to be transcendental. And what is the Jimm of the number pi? It is also another weird number, which also surely is transcendental, but conjecturally transcendental. And Jimm of E is this number, which also must be transcendental. So we tried to see if we could identify these numbers in terms of some algebraic expressions and rational numbers, etc. And we run the PSLQ algorithm on them, but we failed to recognize these numbers. So these numbers appear to be totally new constants of real numbers. Thank you very much for your attention. The ideas explained in this talk have been expounded on several papers, and here are the references. You can contact me if you want any more details. My email is thank you very much again.